You know that feeling when something is just perfect? It works flawlessly, day in, day out, and then bam, out of nowhere, it completely falls apart. Today, we're going to explore the hidden cost of order. It's a core idea from a physics concept you might know, the Harmonic Scale Framework, or HSF. And it argues that stability isn't just a given, it's an active and very finite resource. So let's dive in. So here's the big question, the central puzzle we're trying to solve. We build things to be incredibly robust, right? We're talking bridges, computer chips, even our power grids. We optimize them for absolute peak performance. But here's the weird thing. They often don't just wear down slowly. They work perfectly until suddenly they just don't. So why is perfection so brittle? All right, to crack this puzzle, here's our game plan. We're going to start with this whole brittleness of perfection idea. Then we'll introduce a pretty radical new way to think about energy itself. We're going to figure out why this idea has been hiding in plain sight, and then see how it explains not just system collapses, but maybe, just maybe, the nature of time and gravity. Okay, so let's jump right in by looking at the limits of how we usually think about this stuff. I mean, we're fantastic at measuring energy, but some things that happen in the real world just don't really fit our neat models of everything slowly and gradually decaying. This right here, this is the core problem, and it's not some abstract theory. It's a real practical thing. I mean, think about complex engineering systems that just suddenly go haywire, or stable structures that seem to hit some invisible breaking point. Standard physics is great at describing that it happens, but the harmonic scale framework, well, it offers a much deeper reason for why it happens. So the key, at least from the HSF point of view, is that we have to stop thinking of energy as just one thing. Instead, you've got to imagine that it has two totally different but deeply connected jobs to do in the universe. Now, this is where it gets really interesting. Look at this fundamental split. On the left, you've got dynamic energy. This is the star of the show, right? It's everything we actually measure: motion, heat, light. It answers the question, what happens? But then, over on the right, you've got structural energy. This is the stage director. It doesn't act, it dictates the script. It defines the rules of the game, and it answers a much, much deeper question. What is even allowed to happen in the first place? Think of it this way. A train can have a super powerful engine, that's all its dynamic energy, but that train can only go where there are tracks. Those tracks, they define its admissible state space. Structural energy is the thing that builds and maintains those tracks, making sure that powerful engine stays on a stable, predictable path. So this is the obvious question, isn't it? If this other half of energy exists, this, fundamental architect of reality, why is this the first time most of us are even hearing about it? Well, the answer is kind of brilliantly simple. The whole reason it's hidden is baked right into the way we do science. Our entire toolkit, from thermometers to particle accelerators, it's all built for one single purpose: to detect change. We measure movement, we measure fluctuations, we measure differences. Our instruments are designed to notice when something happens. And this is why it's invisible. The entire job of structural energy is to prevent change from happening. It's like the bouncer at the door of reality, you know? It's enforcing stability, it's forbidding certain events from ever taking place, and it's holding the line saying, nope, that's not allowed to happen here. And that's the punchline. You can't measure something that never happened because structural energy was doing its job. That unstable state never occurred. No weird particle was emitted, no collapse took place, and so not a single one of our instruments registered a thing. It's invisible because of what it does. But we see its fingerprints everywhere. The stability of an atom, the fact that electron orbitals are these clean, discrete levels and not just some random smear, that's a direct result of missing forbidden states. These are all the ghosts of structural energy. And the absolute game changer in HSF is that it treats this stuff not as some passive background rule, but as an active and, this is crucial, a finite resource. So now we have the tool. We can finally solve our original mystery. Why do these perfect systems break so suddenly? Well, it's because their stability isn't free. It's being paid for, moment by moment, out of that finite budget of structural energy. And this just lays it out so clearly. As you push a system harder, more energy, more speed, more complexity, you're basically lighting up more ways for it to behave. Each of those modes needs a piece of that structural energy budget to keep it in line. Eventually, you just ask for more stability than the system can afford. The budget is spent. And at that exact moment, the rules themselves break down, and the system loses what's called admissibility. It doesn't just degrade, it collapses. This is like the hidden tax on optimization. Every single time we add another layer of control, another constraint, or another rule to make a system more efficient or more precise, we are spending from a finite structural energy account. So these highly optimized systems, they're running on a really tight structural budget, and that's exactly what makes them so fragile. Okay, so now let's zoom way out, because this isn't just about bridges and computer chips. The HSF framework suggests this whole dynamic structural split applies to the most fundamental things in our reality. We usually think of time as this constant, universal river that we're all just floating down. But from this perspective, the steady tick-tock of a clock, the very coherence and order of time itself is an active process. It requires constant structural enforcement. And when a system is under structural stress, one of the first things to go is timing. That phase noise, that jitter, it's not just random. It's a sign that the structural budget is getting dangerously low. And what about gravity? It's famously almost mysteriously weak compared to the other forces. HSF offers a wild reinterpretation. What if gravity isn't a dynamic force in the usual sense, but is actually the ultimate structural interaction? What if it's the universe's baseline constraint, a global rule that depends on the entire configuration of everything? That would explain why it's so weak, why you can't block it, and why it's always there, patiently enforcing order on a cosmic scale. So, let's bring this all home. What does this new perspective really mean for how we see the world around us? Honestly, it's a fundamental shift. So, what are the big takeaways here? First, just having a lot of energy doesn't guarantee stability. It's the structure that sets the absolute limits on what that energy can even do. This means when something breaks, it's very often a structural failure, not an energetic one. It also reframes optimization as a clear trade-off. You're sacrificing robustness to gain efficiency. And finally, it tells us that things we just take for granted, like coherence and the very order of time, well, they aren't free. They are actively enforced and they have hard physical limits. And I really want to leave you with this powerful final thought from the source material. Physics, for centuries, has been incredibly successful at explaining the behavior of things, how they move, how they interact, how they change. But this framework suggests there's an even deeper question to ask. Why do stable things exist at all? And the answer, it proposes, lies with this unseen architect, structural energy. Thinking this way just opens up so many new questions, doesn't it? I mean, if stability and even time itself are being paid for from a finite budget, what else is? What other fundamental constants or laws of nature that we see as passive rules are actually active processes that could, under the right conditions, just run out? It's a pretty fascinating thought to chew on.